few more minutes.
Buenos días. Este es el último seminario de los que organizo yo desde el año del año pasado, donde se acaba mi turno de momento. Voy a tocar a Ignacio. So good morning. It's my pleasure to introduce you to Dr. CHELTON, distinguished professor of Earth, Ocean, and Atmospheric Science in Oregon State University. So it's a pleasure and an honor that you have accepted to come to Mallorca to visit us. So this is in the frame of Emotion Project. It's a project that is funded by the Spanish Research Program. And he's going to be here for 2 weeks. So he has a quite busy program. He started, well, yesterday he was in the PhD committee in Roma and the seminar, and then next week he will be time series analysis. So like someone who's still interested, there are some things we have planned to do the course here, but we have about 60 people registered, so we have to find another room in the university, and so now we have a big one, and so if any of you would like to come, just let us know. So Dudley has a very long successful career. He has made significant contributions in different fields of physical oceanography, especially Mesoscale oceanography, which is like equivalent to scale. It's not the scale in the atmosphere, but in the ocean. There are smaller scales in the atmosphere, and also its observation processes with remote sensing. So in scripts. And then affiliated with in California, and just published very relevant paper, prestigious awards. It's a pleasure to host you here.
Thank you for that very nice today. I'm going to present synthesis of things that I've been doing over the last 30 years. Years ago, my research followed two interaction and one looking at mesoscale variability in the ocean. And it was a very rewarding experience about 5 years ago when these two separate parallel tracks merged into one. And so some of what I'm going to talk with you about today is to show the results of bringing together mesoscale oceanography and air-sea interaction. I have a tendency to speak quickly, and that's not necessarily a good thing if English is not your native language. So if I talk too quickly, raise your hand and slow me down. Don't be shy. I'm okay. So, do I have a pointer or just use my finger? I'll use my finger. It's okay. Okay. This is an outline of what I want to cover today. I'm going to start by going back 10 years to when we first started seeing very strong air-sea interaction from satellite scatterometer data and microwave sea surface temperature data. And we'll go from there to more recent work that's been done largely by a former student of mine, Peter Galba, taking the results that we found in frontal 15 years ago, and looking at what those signals look like on over oceanic mesoscale eddies. And I'm going to focus on a particular aspect of Ekman pumping. Everyone here is familiar with Ekman pumping, but I'll define it for you. It's basically wind-driven upwelling in the open ocean. I'm going to show you that there's some terms that are usually left out. Can be come from sea surface temperature effects from air-sea interaction. And then we'll look specifically at what those different contributions mesoscale eddies. And then we'll finish with when the next generation technology giving us measurements on very small scales, which is scales shorter than around 10 kilometers. So let me start with part one of the background, which is, I'm going to get this chair out so I don't trip over it. I keep feeling it against my back. I'm going to fall back over here. This, as I say, dates back quite a long time ago. We first started seeing this sea surface temperature influence on wind speed and on Ekman pumping when we got the very first measurements back from the QuickScat scatterometer. It was very clear in the tropical Pacific. You could see this air-sea interaction propagating westward as tropical instability waves. And after studying that for a while, we went to middle latitudes and found that you could see that signal anywhere that there was a sea surface temperature front. So I'll show you the results of a couple of papers here. There's a lot of papers that have been written on this, and a lot of other people besides me have been involved in it. To show you a movie here. This is the northwestern Atlantic, the Gulf Stream here, the eastern seaboard of North America. And what you're seeing in color here is the wind speed at 10 meters above the sea surface in meters per second. Now I wonder why that stopped. Interesting. That's never stopped before. Try that again. The contours are the sea surface temperature. Let's see if it keeps going now. All right, now it's doing what it's supposed to do. So what you're supposed to see from this, I think it's pretty easy to see, is that the colors and the contours are going together. If I hadn't told you in the titles and from the explanation of it, you might think that these contours and the colors are actually the same variable, but they're not. The contours are the changes in sea surface temperature, and this has all been spatially high-pass filtered to focus on the mesoscale, scales of, say, 50 kilometers to 1,000 kilometers, something like that. And you can see that on those mesoscales, the sea surface temperature and the wind speed over top of it are changing together. Over the warm water, you get high wind speed. That's the solid contours is the warm water. Red is high wind speed. Over the cold water, which is the dash contours, and you get a decrease in the wind speed, which is shown by the purple and blue colors here. And a lot of work has been done over the last 10 years to try to understand the mechanisms for this coupling between sea surface temperature and wind speed. And this is a gross oversimplification of the mechanism. But essentially, what happens is that as a parcel of air moves over warmer water, the heating from below increases the vertical turbulent mixing. And that vertical turbulent mixing brings momentum down from the top of the atmospheric boundary layer to the sea surface. So you get an increase in wind from that mixing effect. Over cold water, on the other hand, you get a stabilization of the bottom of the atmospheric boundary layer. And that stabilization decouples the surface winds from the winds in the top part of the boundary layer. So you get a decrease in wind speed over the cold water. So the wind speed perturbations that are forced by the sea surface temperature are proportional, turns out linearly proportional to the sea surface temperature. And there's a lot of other subtleties to this that I really don't want to go into right now. But the important point here is that aside from that being an interesting coupling, it has some very important dynamical effects. And it has different dynamical effects in the atmosphere than it does in the ocean. We'll talk first about the atmosphere. Suppose that this is an isotherm, sea surface temperature front somewhere in the ocean, and let's say that the winds are blowing obliquely across this temperature front. Then in places where it blows from cool water to warm water, the wind speed increases over the warm water, and so you'll get a divergence over that temperature front. And that divergence is proportional to the downwind component of the temperature gradient. So as you go from cold to warm water, there's an acceleration of the surface winds, and that results in a surface divergence. If the wind were blowing the other way, you would get a decrease in wind speed as you cross the front, and you would end up with a convergence at the sea surface. And those convergences and divergences at the bottom of the boundary layer drives circulations within the boundary layer that affect the winds throughout the boundary layer. It would be nice if those convergences and divergences extended beyond the boundary layer, but most of the studies that have been done to date find that this air-sea interaction is restricted to within the atmospheric boundary layer. There may be some exceptions to that in some places and some time, but for the most part, it's an atmospheric boundary layer phenomenon. What I'm going to talk about today is this pink region here. This is places where the wind blows parallel to a temperature front. And on one side of that front, the cool side, you have a low wind speed. And on the warm side, you have a high wind speed. And that generates a wind stress curl, or a vorticity of the wind, or a curl of the wind stress. And from an oceanographic perspective, that curl of the wind stress is very important because that's what drives Ekman pumping. So just to review here, a divergence would be linearly related to the downwind temperature gradient, and the curls are linearly related to the crosswind temperature gradient. So we'll talk just about the curl. And this is scatter plots for 4 different regions of the world ocean. This is the whole southern ocean here. This is the tropical instability wave region in the eastern tropical Pacific, the Kuroshio extension region, and the Gulf Stream region. And on the bottom axis here shows the crosswind sea surface temperature gradient. And again, this has been spatially high-pass filtered to eliminate the very large scales and focus on the mesoscale, scales of 50 kilometers to 1,000 kilometers. So this is crosswind temperature gradient here, and this is the wind stress curl. And in each region, you see that there's a very well-defined linear relationship. There's more scatter in the northern hemisphere cases here, and that turns out to be not noise in the measurements so much. It's because there's a strong seasonal variation in the magnitude of this coupling between the wind stress curl and the crosswind temperature gradient. It's stronger in winter than it is in the summer, but let's not worry about that. You can see that the lines are linear. They have different slopes in each region. So each region has a different magnitude of coupling, and that depends on a number of different things: the thickness of the boundary layer, the mean winds, mean stability in the boundary layer, and some other things we haven't figured out yet. So the importance of this sea surface temperature induced perturbations of the wind stress curl are that they drive a component of the Ekman. And the conventional view of Ekman pumping, which is very simplistic, is that the vertical velocity from Ekman pumping, it's called the Ekman pumping velocity, is proportional to the curl of the wind stress. And the proportionality factor here, rho naught, is the density of the air, and F is the Coriolis parameter. So the magnitude of the Ekman pumping depends on your latitude in accord with this Coriolis parameter, which varies as a sign of latitude. So from the previous figure, I showed you that sea surface temperature perturbs the wind field in a way that generates curl of the wind stress that's proportional to the crosswind temperature gradient. So if we were to focus on just the sea surface temperature effect on Ekman pumping, it would say that this vertical velocity from the sea surface temperature is linearly proportional to this crosswind temperature gradient, where n is a unit vector in a particular direction, counterclockwise relative to the wind. Don't worry about the details of this. This is the crosswind temperature gradient, and this alpha here is the coupling coefficient. That's the slope of those lines that I showed you in the previous figure. And that slope varies geographically and temporally somewhat. So what we would like to do then is to figure out whether this sea surface temperature induced Ekman pumping is detectable and whether it has any impact on the oceanography. So I'm going to show you a regional example. And the particular region here is the California current system. To orient you here, this is the west coast of the United States. This is San Francisco here. Los Angeles would be down around here. And this is roughly the Oregon, the border between the state of Oregon and the state of Washington. And so in the left panel here, it shows sea surface temperature in color. And there's some contours here, which are the magnitude of the wind stress, and you probably can't see it, but there's vectors, and the winds blow pretty much along shore here in the summertime. This is summer and fall, and this is a September snapshot here. And it's hard to tell from this figure, but there you can see, for example, that there's a patch here of elevated wind stress magnitude over this warm tongue here. And likewise, a cold tongue here, there's a decrease in the wind stress magnitude. But where that becomes clear is when you calculate the curl of this wind stress. And this is a map of the curl of that wind stress. And it's a kind of picture that if you didn't know about this air-sea interaction, you would probably think that this was junk data. Looks like noise in the scatterometer measurements of the wind stress curl. At least when I go way back into the late 1970s, when I was working on my PhD thesis, I was very interested in the winds in this region. We didn't know much about the winds in this region at that time. If somebody had showed me that picture and said, here's a wind data set for you, I probably would have thrown it away because I would have thought it was bad data. But if I take this very same map here and I overlay contours of the crosswind temperature gradient, remember, you go back to this figure here, it says that the wind stress, the curl-driven Ekman pumping should be proportional to the crosswind temperature gradient. If I overlay those contours, you can see that all that stuff that looked like noise is doing exactly what it's supposed to do. This is the contours of the crosswind temperature gradient overlaid on the wind stress curl. So the wind stress curl has a very, very clear signature in this region of the California current, which is a complicated region because there's so much variability in the sea surface temperature associated with the flow of the California current out here, upwelling near the coast, these little streamers of cold water that move offshore, and those sorts of things. So now let me go to background part 2, which is to take these concepts that are very clear in the SST frontal regions, anywhere in the world ocean. I showed you the California current. I could have showed you half a dozen other places in the world ocean. You see just as easily that consistently the curl is proportional to the crosswind temperature gradient. I mean, remember that all this is driven by that air-sea interaction that says that the surface winds are proportional to the sea surface temperature. High winds over warm water, low winds over cold water. So I'm going to show you some results from thesis work of a former student of mine, Peter Galba, and this analysis, it may have come out by now. It's supposed to come out sometime this month in the Journal of Physical Oceanography, so you can find a detailed explanation of this in whenever the January 2015 issue comes out. So this is a picture of a composite average of hundreds of thousands of realizations of mesoscale eddies. In this case, these are eddies that are clockwise rotating here, and these are counterclockwise rotating eddies. If you were in the northern hemisphere, these would be cyclones and these would be anticyclones. This is a region of southward temperature gradient, background mean temperature gradient. So this is mostly northern hemisphere cases here, cyclones and anticyclones. And the structure is not necessarily what you might have expected. We sort of have a notion that mesoscale eddies, cyclones are cold core eddies and anticyclones are warm core eddies. And well, that's true, but they're not simple. This intersection of two lines through zero here is I should mention, these have all been normalized scales so that the units aren't labeled on here. I apologize for that. But this is 1 and 2 radii of the eddy. And so this is all based on some work that we've done that's was in parallel to this automated eddy tracking scheme. These are the eddies that we identified from the altimeter data. So you see that the core of the cold water, it's there, but it's not centered on the center of the eddy. This is in the case of cyclones. In the anticyclones, the warm core, there is a warm core, it's well-defined warm core, but it's also displaced from the center of the eddy. And if you look more closely, you can see in both cases that really what you have is a dipole structure. There's positive here and negative here and positive here. And one of the poles of the dipole is much smaller in magnitude, but there's still a very clear dipole. The mechanism for that is very simple. It's just a simple stirring of the background temperature field. So if we have a southward temperature gradient, it means we have cold water on this side, warm water on this side. If you look at a clockwise rotating eddy, that's going to bring warm water up into this quadrant and bring cold water into this quadrant. And that's what this looks like over here. So this gets complicated a little bit by the tendency for eddies to actually trap cold water and warm water. And if you superpose those two effects, you can reproduce this very accurately. But the dominant mechanism is this stirring. And over in this case of clockwise rotating eddies, you're taking warm water and displacing it up this way from the rotational velocity of the eddy, and cold water gets displaced into this southwest quadrant. Okay, this is for the case of southward background mean temperature gradient. We go to the southern hemisphere and look at cases of northward background temperature gradient, and you get similar structures, except they're mirror images of each other. So now the temperature gradient is northward, and so you have a clockwise rotating eddy is going to bring cold water towards this northwest quadrant and warm water towards the southeast quadrant. And clockwise rotating eddy is going to bring, what is going to do here? The counterclockwise is going to bring warm water down into the southwest quadrant and cold water over here. Okay, so to go back to the air-sea interaction question, now that we know from hundreds of thousands of realizations of mesoscale eddies what the temperature and response to the rotational field, velocity field in the eddy is, we would expect to find low wind speed over the cold water, high wind speed over the warmer water. So everywhere where it's red here, we expect increased wind speed, and where it's blue or purple, we expect decreased wind speed. So we can look at that by composite averaging the satellite measurements of sea surface temperature, exactly the same reference frame that we used for these composite averages of the sea surface temperature. And if I go to the wind speed, that's what it is. And if you blinked, you might have not noticed that there was a difference in these slides. So I'll go back. This is composite averages of temperature, and that's composite averages of wind speed. You know, I've been in this business for quite a few years, and it's pretty rare to see that kind of a correlation on things. So very clearly here, you can see that the sea surface temperature is affecting the wind speed in exactly the way that we expect it to from the mechanisms that we spent so much time studying in sea surface temperature frontal regions. Okay, so that's the air-sea interaction. Now let's also take a look at the wind stress curl response to this effect. So let's suppose that the wind is blowing westerly across these eddies. What would you expect the wind stress curl to look like? I forget which case this is. So, okay. So I'm going to do, I think it's these two cases here, northern hemisphere case, and I'm going to calculate what the Ekman pumping velocity would be for winds blowing from the west across the eddy. So here again is the case for cyclones. This is the cold core eddy. This is the warm core anticyclones. Average over many, many eddies. And this is what the Ekman pumping velocity from the sea surface temperature effect looks like. And so you see here, in this case, you've got warm water on this side, cold on this side, and the wind is blowing this way. You'll get a positive wind stress curl down here, and indeed, you get that positive wind stress curl. On the other side of the eddy, warm water up here, higher wind speed, cold water here, lower wind speed, you'll get a negative wind stress curl. That's a downward or negative Ekman pumping velocity, and indeed you get that. So you get this dipole structure of the sea surface temperature driven wind stress curl, and it's quite clear for both cyclones and anticyclones. Okay, so that really turns out to be only one component of the Ekman pumping. That's the sea surface temperature effect. But there are also surface current effects. And so I'm going to go through a few slides with equations, and just bear with me here. They're not difficult equations, and I'll try to just point out the main points here. In 1965, Melvin Stern wrote a paper on Ekman pumping, and if any of you have ever read Melvin Stern papers, or talked with Melvin Stern when he was still alive, it's really hard to understand anything he said or wrote. But if you persevere and stick through it, stick with it, you'll see that what he really is trying to say is that that equation that I showed you a while ago that said that the Ekman pumping is proportional to the curl of the wind stress, it's not really proportional to the curl of the wind stress. It's proportional to the curl of the ratio of the wind stress over the Coriolis parameter plus the relative vorticity, which is the rotational effect in the eddies. So the F is a planetary vorticity, zeta is a relative vorticity. So F has to do with the rotation of the planet, and zeta has to do with the rotation of the eddy itself. So before, I had no zeta term in here, and this F was taken outside of the curl, and we have 1 over rho naught F times the curl of the stress. But in fact, from the scaling analysis in the Stern paper, the proper way to do that calculation is to take the curl of this ratio. And when you do that, then that turns out to break down into 3 terms. One is the curl of the wind stress that we had before, but now zeta has been added in here. Most of the time zeta is small compared to F, so you can ignore this. And this first term is the conventional view of Ekman pumping. There's 2 other terms in here that I called W beta and W zeta. And W beta is a term that oceanographers are well aware of, and they always throw it away. It's related to the derivative of the Coriolis parameter. So this breakdown into 3 terms is just an application of the quotient rule in calculating the derivative here. So this term turns out to be small because beta is so small compared with F. So this term is usually neglected, and we can neglect it here. But this term we can't neglect, particularly when you get down to mesoscales, and especially when you go to submesoscales. I'm going to show you some pictures. This term here actually dominates the Ekman pumping. It's bigger than any other term. And it's a term that we hardly ever pay any attention to. So, a couple other points on the bottom of this slide here is that we have to keep in mind that the surface stress, the wind-driven surface stress, is not just dependent on the wind speed. It's dependent on the relative motion between the winds and the surface velocity of the ocean. So you can imagine that if the wind were blowing 1 meter per second in this direction and the water were flowing 1 meter per second in the same direction, there's no stress. It's the relative wind that determines the stress. So the stress is proportional to the drag coefficient and the atmospheric air density here, proportional to the square of the relative wind. The relative wind is the atmospheric wind minus the ocean surface velocity. And then finally down here, I've defined this thing called zeta up here, the relative vorticity. And all that is the curl of the surface velocity, of the surface ocean velocity. Now, there are a couple of assumptions in that Stern theory, and they're not trivial assumptions. One assumption is that the Rossby number, or the geostrophic Rossby number, this is the one that we usually think about, and that's proportional to the geostrophic speed, a scaling of the geostrophic speed divided by the Coriolis parameter times the length scale that we're talking about. And the assumption in the Stern derivation is that this Rossby number is small. That's equivalent to saying that the flow is very nearly geostrophic. that the Stern equation also assumes that another Rossby number that oftentimes we don't consider, the Ekman-Rossby number, which is the same thing except that the scale velocity here is the velocity of Ekman currents, wind-driven Ekman currents. Then that ratio over FL is also small. And lastly, the Stern derivation assumes that this relative vorticity is vertically uniform within the boundary layer. Okay, so that's basically the whole story with Ekman pumping, but we might be interested in taking it apart to figure out what it all means. And that is now, this is just repeating the result from the Stern analysis. This is the W zeta term that I said we usually throw a neglect, but it's going to turn out to dominate things. But we really would like to diagnose the various contributions to that wind stress curl. And there are several different contributions. One of them is the sea surface temperature contribution that I talked about before. Another one turns out to be the surface current effect on the relative wind that determines the stress. And there's also some meteorological variability, which we would like to ignore but can't. So we break down this total wind stress into a large-scale background, and we'll assume that that large-scale background has a small curl on the scales of the eddies, mesoscale eddies and submesoscale features that we're interested in. There's a contribution from the relative currents called tau c. There's this contribution we talked about before from the sea surface temperature. And then there's something I call noise, and noise in this case is the meteorological variability on small scales that has nothing to do with eddies or submesoscale features. Let's see. Oh, I didn't mention there's some color coding you can see here, and unfortunately the green doesn't show up very well here. I'm sorry for that, but some projectors it works okay, and otherwise, you see the blank and it can barely read. That's probably tau sub SST. And so the color coding here is that anything that's red has to do with surface currents, anything that's green has to do with sea surface temperature, and anything that's blue has to do with winds. We don't worry about the color coding. The reason for the color coding is for another presentation I gave somewhere where we were talking about combining 3 different satellite data sets. And we wanted to keep track of which satellite would provide which variable. And it gets confusing when you're trying to bring in 3 or 4 different satellites. Okay, so with this breakdown of the decomposition of the stress, then the curl of the stress over this rho naught times F plus zeta is the same scaling factor here times the curl of the current-driven stress plus the curl driven by the sea surface temperature-driven stress, and then the curl of the noise. So we can write down what the expressions are for each of these contributions that are related to the eddy variability. There's an eddy surface velocity, and that's going to drive this W sub c, the Ekman pumping from the current effects. And it's just the rho, this linear proportionality factor of the curl of that relative wind. So if we have the large-scale background wind from a scatterometer or from ECMWF winds or some other source, and we have some surface velocity estimates, for example, that could come from the SWOT altimeter, surface water ocean topography altimeter, which is the next generation, very high resolution altimeter that is hoped it will launch around 2020. Then we have everything we need to calculate this term. The sea surface temperature driven Ekman pumping velocity I've already talked about. It's the curl of the temperature driven perturbations of the surface stress, and that's linearly proportional to the crosswind temperature gradient. Okay. So just to recap what we've talked about, the total Ekman pumping velocity is this W zeta term, which we're going to see is very big. WC term is from surface relative wind driven by surface currents and the surface wind speed. And that's also big on certain scales. There's the WSST, and I already showed you, you can see that very clearly over the California current or any SST frontal region. And it's also significant over eddies, we saw that too. And then there's the meteorological noise. Let's see here. I'll just skip the rest of those words. So without going into details, just want to show you here that decomposition, we have equations for each one of those, and everything is calculable from the right measurements. You have a suite of satellites that measure surface wind, sea surface temperature, and surface geostrophic velocity. You can calculate each of these terms individually. So let's take a look at what this looks like first over mesoscale eddies, and this is more of the work of my former student, Peter Galba. And this is the picture I showed you before for the case of a cyclone, where we had the sea surface temperature anomaly associated with the cyclone. And this was the sea surface temperature-driven Ekman pumping. Now we've looked at what the current induced Ekman pumping is. I'm using the same color scale here for the Ekman pumping velocity for everything. This is a picture of what the sea surface height would look like in the composite average over many hundreds of thousands of cyclones in the northern hemisphere. And this is the term WC, that's the current driven Ekman pumping that arises from the relative motion of the air and the surface ocean velocity. This is the W zeta term that I talked about. That's the term that shows up in the decomposition from the Stern analysis. And this is their sum. So this is actually another contribution of surface currents. This is a contribution from the relative wind. This is a contribution that arises because of gradients in the surface relative vorticity. So you can see that both of these are about the same magnitude, and that when you sum them together, you get this dipole structure that has a slightly displaced set of dipoles, actually it's a tripole, another term shows up in here. And this one on the southern side, this gets reduced by this effect here, this one gets amplified a little bit. So all these are on the same color scale. This is a super saturated color scale here. Not the best choice for that one, but so you can see this, I've chosen that color scale. You can see that this was a lot smaller. It's not an order of magnitude smaller, but it might be a factor of 2 or a factor of 3 smaller, typically, over most of the ocean. So mostly what's happening is these two terms contribute to that total current effect on the right-hand side. And that dominates the Ekman pumping over a mesoscale eddy. So this is the same figure I showed you in the previous slide. This is the calculated Ekman pumping velocity. That's calculated based on altimetry and sea surface temperature from the microwave measurements. I guess that's how it's calculated. Oh, and the large scale winds from the scatterometer. This is the observed Ekman pumping, the total Ekman pumping. And there's an amazing agreement between these two. Once again, you know, if you work with real data, you know, it's a rare treat to have such clear correlations between things. This is calculated based on all of the measurements in those equations I showed you for the decomposition of Ekman pumping. This is what the quick scatterometer saw, and they agree very well with each other. If you look very closely, you'll see that the magnitudes are a little bit higher from the scatterometer measurements, and we don't know for sure why that is, but we think that the reason for it is that the other satellite data from which this was calculated have been fairly heavily smoothed, compared with the smoothing that had to be applied to the scatterometer data. So we think it's just a smoothing effect that's the difference. But the structures are almost exactly the same for both. And this is for the case of anticyclones. It's just mirror images almost of what you find over the cyclone. Again, this is calculated from all of the satellite data. This is observed by the quick scatterometer. Okay, so that brings me to the last part of the talk, which is the future. And the future of really all of the satellite sensors that are under development these days is to move towards submesoscales. We've learned a lot about the mesoscale from currently available satellite data. That's true for sea level, it's for winds, and also for sea surface temperature. And the development these days is to try to push the resolution of all of these different measuring systems to get down to scales less than 10 kilometers, which is a loose definition of the oceanic submesoscale. And the reason that we have reason to expect that things will get very, very interesting when you go to those smaller scales. Don't worry about the left panel here. This is a figure from Pete's paper that shows the sensitivity of the Ekman current-driven Ekman pumping velocity in this axis to the radius scale of the mesoscale eddy. And he only considered down to scales of 50 kilometers because that's the best that you can resolve from the presently available sea surface height fields from altimetry in order to estimate the geostrophic currents and therefore the current-driven Ekman pumping. But you can see that, take the smallest amplitude one, this is for 3 centimeter amplitude eddies, pretty small eddies, not that big. And you can see that what's happening is you get down here around 50 kilometers, this is going up very steeply. So 10 kilometers is somewhere down here, and all of these things are asymptoting off of the chart. And so we can anticipate that the Ekman pumping velocities, when you get down to these submesoscales, are going to be very different from what we're able to see right now. Mesoscales are going to be a whole lot stronger. So I'm going to show you some calculations. We don't yet really have observations of the submesoscale. So for this kind of an analysis, we have to plug our noses and resort to models to try to understand what we can anticipate that we would see if we had adequate observation. And the modeling, I'm going to show you results from 2 snapshots of 2 different models that have been run by Jerome Molemaker at University of California, Los Angeles. And the first case I'm going to show you is a case of an eddy near the Gulf Stream. It's a cyclone that's separated from the Gulf Stream in the model. It's a very high resolution model. It's about a ½ kilometer grid spacing. And I don't want to try to explain the other details of the model. I'm not a modeler myself. But it's a state-of-the-art submesoscale model that Molemaker is working on with Jim McWilliams. And if any of you know Jim McWilliams, you know that he has low tolerance for incompetence. So we can trust that this model is a good model of the submesoscale because it's been endorsed by Jim McWilliams. So the first case I want to look at is this isolated eddy in the northwestern Atlantic that's separated from the Gulf Stream. And I'm going to do a simple calculation, but it's going to be quite elucidating to show you the importance of the various terms on Ekman pumping terms in the decomposition. We'll look at this eddy and just suppose that the wind is blowing a uniform westerly 7 meters per second over the eddy. It wasn't really doing that, but just for the sake of simple calculation, we're going to look at that in that way. And there is a sea surface temperature contribution to the Ekman pumping. Again, there always is. Whenever there's a sea surface temperature anomaly on the sea surface, it drives an upwelling velocity. And we used a coupling coefficient between the wind stress curl and the crosswind temperature gradient that's representative of the northwestern Atlantic. It's actually pretty representative of the whole world, a typical number. Okay, so this is a picture, a snapshot of the sea surface temperature of this mesoscale eddy. And if you squint, fuzzy your eyes a little bit, you see that cold core that you expect in a cyclone. But if you look closely, you can see that there's a lot of interesting structure all around the perimeter of that eddy. And that small scale structure is the submesoscale variability that's associated with this mesoscale eddy. The right-hand panel emphasizes this submesoscale variability by showing the total upwelling velocity calculated from the surface divergence. So this is the ageostrophic upwelling velocity. And it's just simply calculated by assuming that the divergence is relatively uniform in the upper ocean, taking that surface divergence, integrating downward just 10 meters. If I integrated downward 30 meters, I'd get numbers that were 3 times bigger than these. So you notice that the dynamic range in the color bar here is huge. Should have pointed out that the mesoscale things we were talking about tens of centimeters per day, maybe sometimes occasionally a meter per day, rarely a meter per day. But this is 50 meters per day, and these colors are all saturated. So if you actually look at a histogram of this stuff, the numbers get bigger than 100 meters per day. So I'm going to...
That was just a single snapshot, no? It wasn't an average.
Yeah, well, the average would be a lot smaller because they are very transient and they shift around and move. It's probably you could look at it from a Lagrangian perspective and find out that the average is big. But from an Eulerian perspective, looking at a map like this, if you average in time, most of this would go away. I don't have enough images yet to show you the average of time, but I will show you the average of space, which I think is very analogous. Actually, these results have turned out to be interesting enough that they are motivating a much more comprehensive study that Jerome and I are working on. And we'll be looking at 20 days of model output here and look at, among other questions, we'll look at the effects of time averaging. Okay, so this is a review. Go back to the pictures I showed you from Pete Galba's paper, just to remind you of what things look like. And well, this was the structure of the composite average temperature anomaly for global average of the northern hemisphere, hundreds of thousands of realizations of eddies. The sea surface temperature contribution is a dipole. The surface current contribution from the relative wind is sort of a monopole. Really, it's a tripole because it has these flanges on the sides that are of opposite sign, but mostly it's a monopole centered over the core of the eddy. And the W zeta term from the relative vorticity gradient is a dipole, so that the total is a dipole. So we expect to see something like this. And we'll look first at that model output, very heavily smoothed to approximately these scales. It's actually not quite smooth this much, but this is what that temperature anomaly in that cyclone looks like when you smooth to 30-kilometer feature resolution. So it's a monopole sitting here. And for westerly winds, you get the expected dipole structure of the sea surface temperature contribution to Ekman pumping. You get the expected monopole structure of the downwelling in the core over the core of the cyclone in the WC term, with all around the perimeter, it's all red here. That's sort of what would look like a tripole before. And you get a dipole structure in the W zeta term. When you add them together, you get something somewhat complicated, but it looks roughly like this. Remember, this is an average over hundreds of thousands of realization. This is one snapshot. So you have to kind of use your imagination a little bit, but you can see the same kinds of structures that you expect. Now what I'm going to do is telescope down in a succession of improvements of the resolution. So this has been heavily smoothed to resolve features with scales of around 30 kilometers. And we're going to go all the way down to 1 kilometer in steps. So this is 30 kilometers. And this is what the world looks like with 25-kilometer resolution. So go back and forth. There's some changes, but they're relatively subtle. We're starting to see these things are getting stronger. Go from 25 to 20 kilometers, and again, go back and forth between those two. That's, let's see here, I can't control it very well here. That's 25, 20, 15, and they're all changing, but these are changing pretty fast. We go from 15 to 10, and they change quite a bit. So again, do that again. That's 15 kilometers, 10 kilometers. So there's moderately large changes from 15 to 10 kilometers in these two terms. That's really all the changes in this term. This is just the sum of these two terms. These are changing too, but not by nearly as much. Now we'll go down to 5 kilometers, and there's a huge change, just a gigantic change from 10 to 5 kilometers. So it's again 10 kilometers, 5 kilometers. And if you go from 5 to 1, this is obviously a horrible color bar for these kinds of plot, but it shows the relative contributions. These have also gotten big, but this color bar that ranges from -3 to +3 meters per day, which is a pretty good choice for these panels here. Maybe it's not ideal. Maybe we should use a scale of ±5 meters per day, but it's totally inappropriate for this because the magnitude of the upwelling and downwelling on the submesoscale from this W zeta term are huge. So the thing we learned from that is submesoscale Ekman pumping changes very, very quickly on scales smaller than 10 kilometers, which is the basis for defining submesoscale to be around 10 kilometers. Things bigger than 10 kilometers you can think of as mesoscale. Things smaller you can think of as submesoscale. Obviously, there's not a clear, separation between those two, but roughly that's where there's a change in character. So now I show you the cases for 10 kilometers, 5 kilometers, and 1 kilometer. And in the left panels here, I've got the same color bar. Now it runs from -5 to +5 meters per day. And that's the same in all the way down the left and the middle column. But in the right two columns here, I've changed the color bars with each step of smoothing so that it's a good choice for that particular scale of smoothing. So this range is -5 to +5, same as all these other panels over here. This is -20 +20, so it's roughly a factor of 4 times larger, going from 10 kilometers to 5. And this one ranges minus 50 to plus 50, so that's another factor of 2.5 bigger when we go down to those very small submesoscales of 1 kilometer. So that's, yeah.
If you move this map during the corner, you get the other one.
If you do what?
I mean, instead of computing this map from the smooth velocity fields, if you move this Ekman pumping field, you get the same one.
Let me think here a second. I'm going to make sure I don't give the wrong answer on that one. I believe that every term here is a linear term. So it won't matter what order you do it in.
Okay.
So there's nothing nonlinear in this calculation. That's not quite right because there is a nonlinear relationship between stress and the relative vorticity in these terms here. But it's a weak nonlinear term. So it would be very, very close. If you smooth these, it'd be very close to what I showed you.
So if you are interested on the average behavior, I mean, it would be good to just work with the continuous solution.
I think so, yes. I'd like to verify that with some further tests to make sure, but I'm pretty confident that it comes out about the same way. Okay, I'll show you, how am I doing for time? I'm almost out of time, but I'll go quickly through these last three. I just want to show you another dynamical regime here. This is the northern portion of a California current system model that Jerome has developed. We're going to use the same kind of approximations. To be a little more realistic, we're using north-northwesterly winds, which is a typical wind direction in the California current. Same coupling coefficient as what we used before. And this is the region. This is sea surface temperature. You can see there's mesoscale features here. There's a lot of submesoscale structure along the temperature fronts. And that's what the total upwelling calculated from the azeotropic divergence of the surface velocity looks like. A lot of submesoscale structure. And we'll just telescope down like we did before, starting with scales that are comparable to what we can resolve with satellite data today. This is WSST. That's like that California current example I showed you in the SST funnel region. In this case, it's bigger than any of the other terms. But as you telescope down, that's 25 kilometer resolution, 20, 15. You can see these things are growing very big over here. 10, 5, and 1 kilometer. So a lot of interesting stuff here is happening from these two contributions to Ekman pumping, but they're really small compared to this term here, the W zeta term. All right, and this is just a stack plot, again, with special color scales in each case. This is 10 kilometers, 5 kilometers, and 1 kilometer. And the conclusion from that is that, just like in the case of the isolated eddy, the submesoscale Ekman pumping changes very quickly as you go to scales smaller than 10 kilometers. So obviously, if you really want to understand what's happening on small scales, you have to have very accurate measurements of the surface velocity. A point I'll come back to in the conclusions. So what have we learned from all of this? This contribution that I call W zeta, that's from the relative vorticity gradient, comes out of the Stern equation for Ekman pumping, is always a strong contribution to Ekman pumping. It's everywhere strong. And it becomes exceptionally strong when you get down to scales, submesoscales smaller than 10 kilometers. And I'll also just point out that that term is not looked at very often explicitly. In fact, I don't know of any time it's been looked at explicitly until Pete's paper that comes out this month in mesoscales. But it is implicit in any primitive equation model because primitive equation models are forced by the stress. So the stress is in there, the relative vorticity is in there, and so implicitly this term is in every primitive equation model. It's very seldom pulled out to show what its actual contribution is, but it's there. It's not usually present in quasi-geostrophic models because those are typically forced by the wind stress curl or an Ekman pumping velocity that's imposed on the model. And so you won't see that term in quasi-geostrophic models. Likewise, you won't see that term in SQG models, surface quasi-geostrophic models. So it really only shows up in primitive equation models. Very little attention has been given to these contributions from the sea surface temperature and the relative wind effects. But I showed you that they can be big. Depends on the scales that you're interested in. They can be bigger than a meter per day if you get to scales of 10 to 30 kilometers, something like that. And so in general, you can't neglect those, but on the other hand, when you get down to scales below 10 kilometers, they're pretty small compared to the W zeta term. But to follow up on Ananda's point, if you do time averages, these terms WSST and WC are likely to become much more comparable and maybe dominate the Ekman pumping because this W zeta term is very transient and it changes spatially and temporally on relatively short scales. So I think that for future work that people do, all three of these terms have to be kept in mind. And let's see. So I'll finish then with a question, which is that we don't know yet how this W zeta relates to the upwelling calculated diagnostically from the surface divergence field. That W sub divergence that's calculated from the surface divergence has a lot of other things in it, mostly related to internal dynamics. But a large fraction of that divergence-driven upwelling of the surface is probably W zeta. And that's part of the ongoing work that Jerome Mollemaker and I are doing to try to understand how this term relates to that term. Stop there. I just squeezed it into 1 hour.
It's quite warm here. Thank you very much. It was very interesting. I'm looking forward to discuss a lot with you, but maybe questions to the audience.
It's about the composites from the beginning of the SST produced by the Eddies, and why is not symmetric, the positive and negative phenomena?
There's two reasons it's not symmetric. I probably should have included, I could have included a figure. We showed you some simulations we did with a passive tracer. So we took a quasi-geostrophic model and we ran a monopole eddy propagating westward in this region, in a region that had a temperature gradient, latitudinal temperature gradient. And we found we got exactly the same dipole structure in the spatially high-pass filtered fields, except that the leading edge always had a larger amplitude pole than the trailing edge. It happened in the model, it happens in the observations. Not the sea surface temperature, there's a special thing, but for example, in chlorophyll, they go almost exactly the same. So the asymmetry between the leading edge pole and the trailing edge pole is about a factor of 1.5 per passive tracer. I'm not sure why the trailing edge is smaller amplitude, but I suspect that it's because the leading edge has disrupted things. So the eddy is propagating to the west, if you think about a cyclone, so it's going like this, then it sort of stirs up the ambient background field, and then when the eddy moves back into this region, it's no longer undisturbed. So it's a different field that is being affected by the trailing edge. Now, when you look at sea surface temperature, it's not strictly a passive field, because there's a part of the core of the eddy that does tend to trap cold water. So if you, I don't know if is there a pen? I don't see a pen. Okay, I'm gonna, you just have to use your imagination here. So suppose that you have,
I hear you.
oh darn, it might be easier to understand with imagination. So let's say that this is the perimeter of an eddy, and we'll consider the case of, it doesn't matter, we can consider a cyclone or a cyclone, but let's suppose that it's a cyclone in the northern hemisphere, so it's rotating like this. And you get a high here and a low here, and this high is bigger, sort of more concrete. Now you superimpose on that, so this is the same eddy, and it has a tendency to trap, if this is a cyclone, it's going to trap cold water here. So don't confuse H for hot. So now if you superimpose this on that, you can see what happens is that this is going to cool this trailing edge, and it's going to warm the leading edge. You add these two linearly. In fact, I have a figure, I don't have it in my slide set, I'm sorry. But when you add those two together, what happens is that you get a much bigger asymmetry between the leading edge and the trailing edge. So the asymmetry starts out because of just the effect of passive tracers and then rotating edge here. And then it gets modified by this core of that kind of thing. You follow me on that? It's confusing. I'll try to, and maybe if you stick around or when we talk this afternoon, I'll show you a sequence of figures if I can find them on the computer.
No questions?
Why do you have a minus sign going from cold to warm water? You would have a positive sign. So that what would happen is you would get an acceleration. Well, it depends on the. So, can you see this board up here? It's awful dark. I'll try to erase. It depends on what variable you're looking at. So if this is a temperature front, and let's say that it's warm here and cold on this side, then the wind coming up here has some speed and it accelerates. So the coupling there would, for the divergence, would be a positive sign. On the other hand, also in this case, if now we slant this a little bit more this way, then the crosswind component of the temperature gradient here depends on how you define your normal to that, whether it's a positive or a minus. So you're wondering why it's a minus alpha over that. It's because we defined the normal to be in that direction. I don't like that definition, but that's more consistent with the mathematical definition. I like this definition because I like to think of it the way you're thinking of it, which is that you get a positive curl into that.
We have been working in the frame of quasi-geostrophy, and so we have been trying to estimate also vertical velocity for the geostrophic interdynamic effects and comparing what the magnitudes of this vertical velocity with the divergence that we can obtain from the model. And we have seen that at least for mesoscale up to submesoscale, that we can explain about 70% with quasi-geostrophy. We can discuss more later.
How do you get divergence from the quasi-geostrophic model?
No, it's a primitive, so you take primitive equation models, and you can look at the divergence, and then you use this temperature and salinity, and you apply the quasi-geostrophic model with omega equation. Okay. And then you see what's the comparison.
Right.
So it's about 7. And in fact, the velocity that we are getting earlier was the order of 10 meters per day. But for snapshots, when you average, obviously they go down because you have the up and down depending on the dipoles of boiling and down.
So all these things are, I think, really important things to unravel in terms of like future applications of SWOT. And as you know, I gave a presentation last week at the SWOT meeting. It was sort of a modified version of this. Mostly just showed the last figures. But Patrice Klein and Guillaume Lepere were there, and their answer was basically the same as that, is that if you use the omega equation, then you can get the same kind of upline. Well, I think that over the next year or two, we'll probably bring all of this together and try to and begin to understand what the different terms are. But I think that this mechanism may be what shows up in that omega equation. It may be related to this effect.
So that we neglect the stress cut. So the omega equation you don't. So this is something that we have to add back by anti-magnetic signals. So it's something that we have to be missing.
Yeah, well, I have to think it through, but if you start with a primitive equation model, then this is already built into the primitive equation model because it is forced by the stress.
Yeah, but then we just take the temperatures that we need to use the omega equation, and to derive the omega equation, you have to assume that there's no forcing, no wind forcing.
But you're taking a temperature
from
the model that has W zeta in it.
Maybe that's
so it's kind of a chicken and egg thing to try to figure out how it goes through. But if you start with a primitive equation model, it has that W zeta in it. And so some part of what you see might be that mechanism. But again, these are things that Yeah, these are things that I hope become clearer over the next year or so. And in addition to the work that I mentioned with Jerome, Patrice is very interested in, and we all are interested in trying to understand how their analysis relates to this. Right now we don't know, but these terms are big. They're the same size of the terms that everybody else is talking about, and so they, and there's some overlap between them for sure.
I would like to add also in relation with that. I think that also for the pseudoscopic theory, or in this case, I understood well for the Ekman quantity, for a scale smaller than 10 kilometers, Rosby values can be 1, not much smaller than 1. So maybe we have to think more on that.
Absolutely. In fact, I have another slide here. It's a list of questions, but I don't want to. Among those questions is that one, is what happens when you go to those small scales where the Stern approximation breaks down, because it assumes small Rossby numbers, as you say, but so does SQG. So, it's not like we have a special problem. We all have that problem. My intuition is that this W zeta term is still going to survive in a very similar form when you go to those smaller scales, but that geostrophy is not going to survive. So I think that the SQG is going to lose all of that. I mean, McWilliams says SQG is not useful at scales smaller than 10 kilometers, but you have to go to primitive equations. Maybe it's 15 kilometers, maybe it's 20, but it's somewhere in that range, somewhere 10 to 20 kilometers. So my colleague Roger Samuelson is trying to work on extending the Stern theory without making those assumptions for small Rossby. And there's also another assumption that I mentioned. It assumes that the relative vorticity is uniform in the upper water column, and that's not going to be true either on these submesoscales. So there's some modifications. It's a great opportunity for theorists and modelers and observationalists to get together and figure it all out. But this is raising a lot of questions that haven't been raised before. So I think it's going to be a useful part of the conversation about upwelling in these small scales.
So what would be for SWOT measurements? If we have a resolution of about 5 kilometers, then we are in the submesoscale, but they will provide SSA, C-surface height, and how we estimate velocities.
So I'm worried about SWOT. Yes, it's going to provide 5 kilometer measurements of sea surface height, but that W zeta term is a derivative of relative vorticity. So going from sea level to velocity, there's one derivative. From velocity to relative vorticity, there's another derivative. And to the gradient of relative vorticity, there's a third derivative. So in order to get a W zeta term from SWOT, you have to calculate triple derivatives of a noisy sea level field. And that noise is going to be amplified. Anytime you calculate a derivative, whatever noise you have gets bigger. So my suspicion is that we aren't going to come anywhere close to 5 kilometers with SWOT for that term in the upwelling phase. We might not even be able to do 20 kilometers with SWOT. But that's still a factor of almost, well, it's easily a factor of 3 better than we can do right now. So there's no doubt that we're going to learn a lot about the mesoscale that we don't know right now. But I'm reserved in my opinion of how much we'll get on scales of 5 kilometers. I think that that's going to be pushing SWOT a little too far. On the other hand, I've been involved in satellite remote sensing for more than 30 years now. And every satellite that's ever been launched has always proven more accurate than the specifications prior to launch. So if we think that SWOT can do 5 kilometers now, it may turn out after launch that it can do 2 kilometers with the accuracy that we're thinking of right now. If that's true, then that opens up the window closer and closer into the submesoscale where we can see it. There's more simulations can be done by putting in realistic noise and doing those triple derivatives and understanding what the resolution limitations are. This is all part of this ongoing thing. So this will keep me busy until I really retire.
And about the in-situ observations, like you said, that we don't have in-situ observations for the submesoscale. What do you think about gliders? The gliders provide us quite high resolution measurements with
Well,
air flow.
sure. Right. I'm sure that a lot could be learned from several gliders over a restricted domain where you have a lot of these submesoscale features. Things like we have in the Mediterranean, or things like we have off of the California, Oregon coast. There's a lot of submesoscale structure there. And I can envision a day when people are doing experiments with, say, air SWAT. This is an airplane-mounted SWAT altimeter system, and in situ measurements to make the below surface measurements of all the various variables. So I think that gliders will be very useful for that.
I just had now a very general question about you have a long career as a professor and a researcher. So would you like to give some advice to the young people? Sorry, because I didn't.
Yeah, I'm sure that I could give all kinds of advice. But I suppose the most important thing is don't worry so much about the future, because I remember in my early days thinking, wow, you know, am I going to be able to do this for 30 years? And 30 years later, it's like, wow, can I do this for another 20 years? And it goes by fast. And if you're doing good work, and so the second piece of advice is, first, don't worry about the future. Second is, never lower your integrity. So, and by that I mean, you know, don't try to pretend that you know something more than you do. And there is a great tendency, I know, I work with young people, and young people, everybody wants to do something that will make them famous. Don't worry about that. That will come with time if you're doing good work. And if you spend your time trying to make yourself famous, you're going to come across as what we call in the United States a used car salesman. So used car salesmen, they sell cars and they don't tell you the truth, you know, and you can't really trust them. So you don't want to ever get into a situation where people lose their trust in what you've done. So don't ever say more than you know about something. Because once you develop a reputation in your career as saying more than you know, then you're not trusted by other scientists who know that once you said more than you knew, and so now they don't know whether what you're saying now is more than you know. So that's what I mean by integrity, is keep your integrity, keep your nose down, keep doing good work, and hope for the best. And 30 years will go by a lot faster than you think it will. I don't know if that's helpful, but that's...
Thanks for the comment. Just one thing that when you show the composites of the SST, we also show the composite of the wind. So the wind is intensified in the same places where SST is. So isn't this a mechanism for having a feedback on your eddy velocity? So maybe you can have a positive feedback sometimes or negative. So you can I guess it depends on the wind direction.
Well, I think the feedback comes from the Ekman pumping. You think that this is quasi-geostrophic, so what's going to determine the dynamics is the vorticity that's input from the wind. So it is that WC term and the WSST term. And I have some other figures. Are you here or are you at the university?
No, I'm here, but not this afternoon. But I will come to the course next week.
Yeah, so I'm going to give probably a short 15-minute seminar to a group of people here about some modeling work that I've been doing with a group at Oregon State, where we've imposed this sea surface temperature effect and the surface current effect on three model runs. There's a control run that has none of this feedback. There's a run that has the SST terms only, and it has another run that has the current effect. And we're looking at how it changes the eddy structure. It's all through that Ekman pumping feedback.